Okay, welcome everyone. Today we're very happy to have Nathan Benjamin giving us a talk. This talk is about Narain to Narnia. So please take it away, Nathan.
Okay, thanks so much, Nima, and thanks very much for the invitation to speak here. It's really a pleasure. The title of my talk is Narain to Narnia, but despite this title, the first half of this talk will take place on Earth, and only in the second half will I explain the title and we go to Narnia. So please be patient with me. And this talk is about some upcoming work that will appear in maybe 1 or 2 weeks with my collaborators, Christoph Keller, Hiroshi Ooguri, and Ida Zadeh. Okay, so let me start with some big picture motivation of what we're going to be thinking about in this talk. The big picture that I'm going to have in the back of my mind in this talk is what is the role of averaging in ADS-CFT? And when I say averaging, there are two things you could mean by averaging, and they're sometimes called self-averaging versus ensemble averaging. So self-averaging is quite an old story in holography, where you take a single unitary healthy CFT and you average over some states in the theory. So for example, maybe you average over some high energy states of the theory and you get some universal behavior, which can have some nice gravitational interpretation. So one example of this would be the Cardy formula for 2D CFTs. There, if you take any CFT and you go to sufficiently high energy and you smear over some density of states and just look at the entropy, the answer is universal. It only depends on the central charge and the energy, as long as the energy is sufficiently high. And there's quite a beautiful gravitational interpretation of this universal formula, which is it's the black hole entropy, which should also be universal. That's not the kind of averaging I'm going to talk about in this talk. Instead, I'm going to talk about what's called ensemble averaging, where you really take many, many different CFTs and you average over those. And this is a little bit unusual to do. So in the most well-understood examples of ADS-CFT, like for example, n equals 4 super Young-Mills, you don't do any of this averaging. You just take a single CFT and there's a single gravitational interpretation. But in recent years, these ensemble average theories have been considered for various reasons. The most famous of which is, it was shown a few years ago by Saad Shankar in Stanford that a two-dimensional theory of gravity called J-cube tidal bone gravity is dual not to a single unitary quantum system, but some average over matrix models. And that leads to a natural question, is this simply an accident of low dimensions, or maybe can we get some similar statements about average holographic duality in higher dimensions? And the smallest number bigger than 2 is 3. So I'm going to look at this question in the context of ADS3, CFT2, and ask if there's some kind of averaging holographic duality there. Okay, so last summer, there were two very beautiful papers written about precisely this subject. One by actually the host of this seminar series, Nima, and collaborators, and another by Maloney and Witten, where they proposed some holographic duality between an average theory of C-free bosons. So they took C-free bosons in 2 dimensions, averaged over their conformal manifold, and they argued that this theory is dual to some Chern-Simons-like gravity theory in 3 dimensions. So I'll describe these 2 papers in a little bit more detail, but roughly speaking, what they did was they computed the average partition function of these C-free bosons, and they showed that it was equal to the partition function of this sort of exotic gravity theory in ADS3. These papers were just at the level of the partition function of these C-free bosons, which are the same. These are sometimes called Narain theories because they were first studied by Narain in I guess the 80s or so. And just a roadmap of where I'm going to go. In this talk, I'm going to generalize this proposal of Nima et al. And Alex et al. In 3 different ways. First, we're going to look at, instead of free bosons, we're going to look at orbifolds of free bosons and look at their average partition functions. We're also going to look at their average correlation functions. We're going to find that there's some nice interpretation in the bulk for the average 4-point functions of some operators that didn't show up in these 2 papers earlier from the summer. And then we'll discuss attempting to generalize this to more interesting CFTs, which have conformal manifolds, in particular some supersymmetric theories, which also have exactly marginal operators. So instead of looking just at free theories or orbifolds of free theories, we'll see if we can look at some average like K3 partition functions or Calabi-Yaus or things like this. And just so I'm not accused of like pulling a fast one, this last part will be unsuccessful, but I think it'll be unsuccessful in an interesting way. Okay, so a brief outline of the talk. First, we'll review the paper by Nima and friends and Alex and friends. Then I'll discuss averaging the orbifold theories, averaging correlation functions in the orbifold theories, and possible generalizations to interacting supersymmetric theories. So before I go on, maybe I'll stop if there are any questions. Okay. So first I'm going to review these two papers from about last summer about averaging Narain theories. And fortunately, Nima is in the audience, so he can correct me if I say anything egregiously wrong. So let's consider maybe the first CFT that many of us look at, the C=1 free boson, which is in like chapter 2 of Polchinski. So the action of this theory is very simple. It's just a free theory. You have a scalar field X, which we identified with X plus 2 pi r. So it's a compact free boson. This theory has U1 times U1 global symmetry. You can see that there's a current, a 1,0 current on the left and a 0,1 current on the right. And because this theory is free, this marginal operator dx dvar x is exactly marginal. So if you perturb by it, all you do is you get another free boson at a slightly different radius. So this theory has a conformal manifold that's labeled by the radius r. Moreover, once you have this conformal manifold or moduli space, there's a natural measure on this moduli space coming from the Zamolodchikov metric. You just compute the 2-point function of this dx dvar x operator. And if you do this computation, you get that the natural measure is, the natural metric is this. One way to see that this is reasonable is that you can see that this is invariant under T duality, which takes r to 1 over r. So we have a natural measure. So then you can ask, given this measure, what's the average free boson CFT for some reasonable physical quantities, such as the partition function? So because this theory is free, we can compute the partition function at any point for any radius. And this is a famous exercise. So I'll just roughly say what the answer is and where it comes from. There's this piece 1 over eta of q, where eta is this Dedekind eta function defined here, which are just the oscillator modes that we see. But the theory also has some non-trivial momentum and winding states, which you can think of as like if the string has some quantized units of momentum or winding. And if you work out what the energies are and the momentum, et cetera, you get that this is the partition function of the free boson at some radius r. You can check that this has all the nice properties we want. It's modular invariant. If you expand it into the characters, you get positive integer degeneracies, et cetera. And so now we can ask what the average partition function is, where we average over the moduli space, namely r. So we're just going to take the measure coming from what Zamolodchikov told us and take this answer, which we know exactly. We integrate from 1 to infinity because I don't want to overcount. There's this r to 1 over r symmetry from T duality. So I don't want to double count. For C=1, that doesn't matter. That's just a factor of 2. But later on, when we go to higher C, it'll be a factor of infinity. So it's important to just integrate over 1 T duality orbit. And since we know this answer exactly, in principle, we can just do this integral. Actually, this integral diverges. You can convince yourself that at large r, this z is proportional to r. So this diverges rather badly, but that's fine. At higher C, it will this won't happen.
Can we go back?
So, yeah.
Why do we need to integrate over the whole region of R? Can't we just average over some small region and explore what happens?
Absolutely. Yeah, you absolutely can. I mean, you can do whatever you want. I think so what we're going to do is we're going to integrate over the whole moduli space because there's not really a natural place to sort of stop, but you could absolutely integrate over, whatever subspace of moduli space you want to. Okay. So, and in fact, once we get to higher C, then this divergence will go away. Okay, so a natural generalization is to consider C-free scalars. So the most general action looks like this. Okay, there are a lot of indices, but it's not that scary. These alpha, beta are the worldsheet indices. They just go from 1 to 2. And P and Q are the space-time indices. They go from 1 to C. And we can have a symmetric term and an anti-symmetric term. This is still a free theory, so you can still exactly solve it. And this GPQ is some symmetric C by C matrix, which from the 2D theory is just a coupling constants. Okay, from the space-time, it's symmetric, but that won't matter for this talk. And here's a C by C anti-symmetric matrix. So now this theory has more symmetry. There's U1 to the C times U1 to the C symmetry. And you can see the conformal manifold is much bigger. It's labeled by this G matrix, a C by C symmetric matrix, and a C by C anti-symmetric matrix, which is C squared dimensional. And Narain worked out what this moduli space is. It's given by this double coset. And again, you can compute the Zamolodchikov metric on this moduli space, and this will give you a natural measure to look at. So again, now we can compute the partition function at every point in this moduli space, namely every G and B field. it's some oscillator modes and some momentum and winding sum, and you can compute the average. You can actually do this calculation directly, like it's a free field theory, it's not so bad, but there's some tricks, like you can show that the average has to obey some certain differential equations, which have a unique solution, etc. And if you're interested, we can discuss it afterwards, or you can read either of these two papers. But I'll just tell you what the answer is. The answer converges, and it's given by this expression right here. Okay, so let me say what this expression is. Here's the oscillator modes. These have to be there because at every point in the moduli space, they're there. And this E function is what's called a real analytic Eisenstein series. And what it is it's just the modular sum of some particular object. This average has some nice properties. First of all, it's modular invariant, as it has to be, because every individual theory is. And if you decompose it into the characters, you get some positive continuous decomposition now. Okay, so this is just some formula. I'm gonna try to give some more intuition for it. First, I'm gonna rewrite it as the following. Using some of the properties of these functions, you can show that the average is given by the following. You take all of the oscillator modes, which is this 1 over eta to the 2c, and you do a sum over SL2z, a modular sum over this over these oscillator modes. So roughly speaking, that means that the average partition function for these C-free bosons is the modular sum of the shared chiral algebra. This 1 over eta to the 2c is the shared chiral algebra at all points in the moduli space, and you do the modular sum, and then you get the average. So let me give some rough intuition for why this is not a crazy answer. So what properties should the average have? So if there's some feature that's shared at all points in the moduli space, then the average better have it as well. And there are two features that I'm going to point out that are shared at all points. The first one is they all have a shared chiral algebra, their backing block. And the second is the final answer is modular invariant, because every point is modular invariant. And this answer in some sense is kind of like the simplest thing you could guess that has both of those properties. You start with the thing that they all share, their chiral algebra. That can't possibly be the average because that guy's not modular invariant. And so the dumbest thing you can do to make it modular invariant is to sum over its orbits. It's not guaranteed that that was the right answer, but it turns out that is the right answer in this calculation that I guess Nima and friends did. Oh, by the way, I should mention that secretly this calculation was done in the 20th century by the mathematician Siegel, but he did it, interpret it in terms of lattice theta functions and whatnot. Okay, so now we have this formula for the average partition function. And there's a question of, is there some gravitational interpretation for the sum? And what Nima and friends showed is the answer is yes, if you allow yourself some leeway in what you mean by gravity. So here I'm going to write this answer again. And what we're going to interpret it is that in this sum, we're going to interpret it as a different bulk space-time geometry. And this summand is going to be the action of some Chern-Simons-like theory. So what we're going to do is we're going to do a sum over geometries weighted by some action. So it turns out that this sum is precisely the sum that you would do if you wanted to do a sum over classical solutions in ADS3. What they do is what they correspond to is thermal ADS3 or any class of BTZ black holes. So in the next slide, I'll say that a little bit more. And the summand is what you would get by evaluating some abelian Chern-Simons theory on each geometry. So let me say this in a little bit more detail. We're going to classify all hyperbolic geometries with some fixed conformal boundary to be some genus 1 Riemann surface. So two of these are thermal ADS3. So here there's a contractible spatial circle. And what you can do is also you can consider the Euclidean BTZ black hole, which has contractible Euclidean time cycle. And more generally, you can take any linear combination of the spatial and time cycle to be contractible. These are sometimes called the SL2Z family of black holes. And if you work it out, these correspond precisely with this sum that we're doing in the previous slide here. And this summand, yeah.
Can you clarify? These are not all hyperbolic three manifolds with a torus boundary, right? I mean, you could do something much more complicated than just this handle body.
At genus 1, I think there's maybe I need some more adjectives, but at genus 1, there's this theorem that with some fixed complex structure tau, if you have some three manifold that emits hyperbolic metric with this conformal boundary, then they're classified by the handle bodies. At higher genus, that's not true, but at genus 1, it is true.
Okay, I guess I must be confused then.
Yeah, at higher genus, it's more subtle, and that's actually a very interesting question about what to do with these non-handle bodies. But Yeah, we can discuss that. Okay, so let me just summarize the recent papers by these people. What these guys showed is that the three quantities are the same. The average partition function of C-free bosons, the modular sum of the shared chiral algebra, and some bulk Chern-Simons theory where we sum over bulk geometries with fixed conformal boundary. Okay, so now let's try averaging over orbifolds. So recall that every Narain CFT has this Z2 global symmetry where you take all of the fields X to minus X. And we can orbifold by this symmetry. So just an example in case people aren't quite familiar with this, at C equals 1, these are the S1 mod Z2 orbifold CFTs. So maybe some of you have seen this diagram before, but this is the space of all possible C equals 1 theories. This is the S1 branch, which we looked at before. And there's a one-to-one correspondence between this branch and this branch where you just orbifold by the Z2. And we're going to discuss averaging over this orbifold branch. So this theory was, these orbifolds were studied like, I guess in the 80s. And the partition function is very simple to compute. What you basically do is you project onto states that are invariant under the Z2, but then you're not done yet. You have to include what's called the twisted sector of the Hilbert space. Or you can think of it if you have a string starting and ending at 2 points that are identified under the Z2 action. And if you work it out, the orbifolded theory is the partition function is given in terms of the unorbifolded theory plus these states, which are sometimes called the twisted sector states. You can work this out, like whatever. The only point I want to make is that these twisted sector states are completely moduli independent. They don't depend on the G and B field or the radius or whatever that you turn on. And they're just these terms over here. And you can ask now, what is the average of these Z2 orbifolds? And actually this calculation is very, very easy to do. It's basically the same calculation that we did in the previous slides, because these guys are moduli independent, so they just come along for the ride. There's one thing you have to check, which is that the measure is the same on the orbifold branch as it is on the unorbifold branch. But roughly speaking, it is because the marginal operator dx bar x doesn't get projected out when you do the orbifold. So that means that when you take the average over the G and B fields, you just get the average of this guy, and these three guys just come along for the ride. So the average is very, very easy to compute, and it's just given by this combination over here. I'm going to write again here. So now there's a question of, is there an interpretation of this average as a sum over geometries? So remember that last time, or in the previous Narain examples, what we did was we took the vacuum character, take its mod squared, and did its SL2Z sum. So is the same thing true for the orbifold theories? So the vacuum character of the orbifold theory is very easy to compute. It's a little bit different than the Narain theories because roughly speaking, we threw away half of the currents from the Z2 orbifold. Okay, if you work it out, it's this, okay, whatever. It's this combination here. And so here's a question, which is the average of these orbifold theory just the modular sum of this vacuum block squared? We know both sides of this equation. We can just compute both sides and compare.
Can I ask a question?
Yeah, absolutely.
This is Jeff Harvey. Hi. What's the defining property of the orbifold theories? For the Narain theories, the defining property was that you had a U1 to the C times U1 to the C current algebra.
Yeah.
What's the defining property of these, and how do you know you're summing overall theories with that defining property?
Yeah, fantastic question. One way I can define it is very similar, which is now instead of the vacuum character being generically, meaning all except measure 0, this U1 to the C, now it's this algebra, which has this different character here. So for a generic all except measure 0 being when you get extra currents from the momentum and winding sum states, these orbifold theories will just have this as this vacuum block.
Is there a theorem that says that only orbifold theories have that vacuum block?
I don't know if it's proven, but I would expect it to be true. But I don't know if there's a theorem saying that.
Okay, thanks.
I'm actually not sure if there's a theorem saying that for Narain. Like maybe yeah, for U1 to the C, I'm also not sure if you can prove that the only theories with U1 to the C symmetry are the Narain theories.
Yeah, I'm not aware of such a proof, but it's
probably true.
Believed.
Similarly, I would expect this is also true.
Thanks.
Yeah. Thanks for the question. Okay. So great. So so now we ask is the average of these Z2 orbifold theories given by the modular sum of the vacuum character squared, and the answer is no. you can just compute both sides of the equation, and they're just not equal. Okay, so before we derive the right prescription, let's try to guess it again. And to do this, I'm going to review some facts about the representation theory of these orbifold theories. So I'm just going to tell you some facts. These are not difficult to derive. This is, I guess, related to what Jeff was asking. These orbifold theories have a partition function given by the following. They of course have their vacuum character squared, but they also have some states that are always shared that are still moduli independent. These are different. These are not in the vacuum block. They're different representations. And roughly speaking, they correspond to the twisted sectors. I give some explicit formulas here, but they're not so important. They're just so you can see that these formulas exist. And all of these orbifold theories have these moduli independent pieces, which correspond to not just the vacuum block, but also some twisted sector states, which come along for the ride. All of the moduli dependent parts in these theory come from the momentum winding states, which I write over here. And roughly speaking, there are like half as many of these guys as there would be in the Narain theories. They're like the cosines survive, but not the sines or something. So the intuition that we sort of had from one hand wavy argument for the explanation of Nima et al.'s results was that you take the thing that's shared by all points in the moduli space, which for the Narain theories was just the vacuum descendants, and then take their modular sum. But now you see for the orbifolds, there are some things that are shared that aren't in the vacuum block. One easy way to tell they're not in the vacuum block is they have different conformal weights mod 1, and characters always have to have the same conformal weight mod 1. So what we can do is we can take these moduli independent pieces and say, well, maybe let's try the modular sum of these 4 guys. Okay, so proposal. The average partition function is not just given by the SL2Z sum of the vacuum block, but also all moduli independent pieces. And the answer is yes. If you do this sum, you get the right answer. Okay, great. So now we have a sum that looks like this, which means that we should ask if there's some holographic interpretation of it, where we sum over classical saddles of ADS3. And we're going to give one. So now we're going to consider an abelian Chern-Simons theory, but instead of just U1 to the C, we're going to gauge the discrete Z2 symmetry that takes A to minus A. So now we're going to compute this action on all of these different bulk geometries. And am I frozen? Oh no, I'm sorry. The way we do that is first we have to project onto the Z2 singlet sector states. And if you do that, you do this computation, you get these combinations of the chiral algebra. But you're not quite done yet. You also have to include vortices coming from sort of defects in the bulk theory. In particular, there are these one-dimensional line operators in the bulk that you now have to include, where the gauge field picks up a holonomy A to minus A when circling them. So as a cartoon, it looks something like this. Here's some 3-dimensional bulk. In the middle, I have some defect. And as the gauge field circles it, it takes A to minus A. And we need to compute the partition function of this Chern-Simons theory on this geometry where we have this non-contractible cycle running through. So again, I'll just tell you the answer. If you evaluate the Chern-Simons action here, you get this combination of etas and betas. And this also needs to be included when you consider the partition function. So finally, putting it all together, in one geometry, in thermal ADS3, we get these combinations of characters of the U1 to the C mod Z2 algebra. Okay, I wrote this in small font, so you can't read it, but it's in principle some computation that you can do. And now, sort of by fiat, we also say that we don't just compute this on a fixed geometry, but we have to include a sum over geometries, which will give us this sum over SL2Z of the modular images of this guy here. And this precisely reproduces the average of the U1 to the Z2 orbifold of the U1 to the C theories. Okay, so there's more to life than Z2 orbifolds.
Right,
you might at this, yes.
Can you say again what the different terms were in ADS? Yeah. One of them was the term with the defect inserted.
Yeah, the last two terms.
The original.
The last two terms were.
And the first two terms just come from computing.
Without defect, but projecting onto Z2 invariant states. These two terms you also have to project onto Z2 invariant states as well. Schematically, it's very
means
similar
A
to the
goes to
contribution. Sorry?
Z2 projection of the Chern-Simons field now.
That's right. That's right. The A to minus A. So just the even states.
Okay.
At this point, you might have said that this computation is a little bit, it's in some sense a little bit cheating because it's very, very similar to the computation done by Nima et al. Over the summer, because the moduli space of the Z2 orbifold is precisely the same as the moduli space of the unorbifolded theory, because there's a one-to-one correspondence between a unorbifolded theory and the Z2 orbifold. So we're still averaging over kind of the same moduli space, where there's just a different theory associated to each point. There are other orbifolds we could consider, because there are some very special Narain theories which have some enhanced symmetry. So one simple example is if you take a T2, so two free bosons, and angle them at like 120 degrees, you can also have a Z3 symmetry when you take the complexified boson and rotate it by e to the 2 pi I over 3. So we can consider some subspace of Narain moduli space where there's a Zn symmetry given by this sort of crystallographic lattice. So as an example, we're going to consider these theories where there's either Z3, Z4, or Z6 symmetry. It turns out for this symmetry where you rotate it by 120 degrees or 90 degrees, you need the central charge to be even. And roughly speaking, what you're doing is you're fixing the complex structure, and then you're allowing the Keller structure to change. So roughly speaking, what you're doing is you've lost half of your degrees of freedom. So instead of C squared dimensions, there's like C squared over 2 dimensions that you're allowed to average over. So this is qualitatively different from the Z2 case because the moduli space is different from the Narain theories. This is another computation you can do. I won't bore you with the details, but we get a very similar result for the average, even though the moduli space is different. What happens is the average of the T2D mod Zn CFTs, where now we don't average over all of Narain space, moduli space, we only average over the Narain moduli space that admits this particular Zn action, is again given by the modular sum of all of the moduli independent pieces, namely the vacuum, the untwisted sector, descendants, and all of the twisted sector states. So basically everything other than the momentum and winding sum. You take these guys, you do their SL2Z sum, and you get the average. And now we're averaging over sort of a subspace of moduli space. Okay, maybe let me pause if there are questions, and if not, we'll go to Narnia soon. Okay, so it's important to keep perspective in life of what the big picture is, and there's a lot more to life than the partition function. There's also correlation functions, and we can ask if there's an interpretation of average of correlation functions in these Narain theories. And in the original papers from this summer, they only kind of looked at partition functions, and I think there's a pretty good reason that they did. Here's a rough intuition for it. Let's go back to the Narain case, the U1 to the C theories that Nima and friends looked at. What was the bulk theory? The bulk theory was this Chern-Simons theory that only knew about the U1 to the C vacuum descendants. And those correspond to all of the uncharged operators in the vacuum block of the CFT. And all correlation functions of those are purely kinematical. They don't depend on all of the moduli, right? The correlation functions of descendants of the U1 to the C current algebra doesn't care what radius you are at because it's all encoded in the block. So the bulk sort of doesn't know about the charge states, which are moduli dependent. So you might not really expect there to be an interesting average when you look at those. And indeed, you can compute the charge particle 2-point functions, say, and you can compute their average, and we didn't find any good interpretation. But the orbifold case is actually quite qualitatively different because there are some states that are, in some sense, they're shared. The twist fields are shared at all points in the moduli space, but the twist fields now are no longer in the vacuum block, so they know about the moduli. In particular, if you look at the 4-point function of 4 twist 2 fields in the Z2 orbifold case, that knows about the moduli. So you might hope that there will be sort of the Chern-Simons 2 will then be smart enough to know something about this average. So now I'm going to compute for you what the averaged 4-point.
Sorry, Nathan, I just got confused by
yeah.
that. So for the the correlation functions that don't depend on the moduli, you say it's okay that the Chern-Simons theory doesn't know how to compute them? That sounds
no,
bad.
no. There it does, but nothing interesting happens because there's no interesting average. Yeah. So
what are they in the what are they on the Chern-Simons side?
That's a good question, I guess. I wonder if it would almost be kind of automatic because this Chern-Simons just knows about the vacuum descendants, and the vacuum descendants, all the correlation functions of vacuum descendants are just determined from the commutator algebra. I don't have a sharp answer for you, but I think it should not be difficult to interpret it. But it doesn't know about any sort of interesting moduli dependent guys. It wouldn't know about. And these twist fields are one example of, are sort of the first example of some interesting moduli dependent correlators that you would see.
So the correlation function, what part of these operators is moduli dependent? Their dimension, the correlation function?
The correlation function. The dimension is not. The dimension is just going to be proportional to C. But this 4-point function I write down here. So I'll just flash the next slide and I'll go there. But you see there are G fields here, and so this metric will show up when we compute the 4-point function. So that's something that will not show up if you look at.
So how should we interpret what we think the dual gravity-like theory should be able to compute? I mean, in general, if we have a CFT that depends on moduli, the spectrum will depend on the moduli. So we might not be even able to track operators. Maybe we can track them in small regions, but not over the whole moduli space.
Yeah, and indeed for the spectrum, we're only able to track sort of the average spectrum, right? What this calculation of Nima et al. Did was they computed the average spectrum of this moduli space, and that was what the Chern-Simons theory knew about.
Right, but so then generically speaking, what would one expect that there's any correlation functions that one can talk about, or is it just special because you have some operators whose dimensions are stationary that you can track?
I think it's more the latter. I think it's if there's some operator that's sort of the same everywhere in the moduli space, like this twist 2 operator, the same dimension everywhere in this moduli space, then this correlation function we can interpret. But I don't know the rules. We're just sort of exploring and seeing if we can get any interpretation. Like we don't have some more fundamental explanation of it. So in some sense, what we're doing is kind of exploring and seeing what interpretations we can get. And for these twist operators, we'll be able to. Okay, yeah, thanks for the question. Okay, so now we're going to look at the 4-point function of this twist 2 operator. So let me just review some facts about these twist operators. They're labeled by a fixed point in your orbifold. And there are 2 to the C different fixed points, roughly speaking, because for every dimension, you can be at the point 0 or the point 1/2. So you label each of these twist operators by some vector in Z2 to the C. And you can sort of by convention set one of them to be at the point 0. And you can show that this correlator only does not vanish if the sum, there's some sort of charge conservation, if the sum of these 4 vectors is equal to 0. So this is the most general 4-point function of twist 2 operators you can write down. And we need to compute what it is and then do the average. Well, fortunately, we don't need to compute what it is because that was done in the 80s. There are some well-known techniques of computing this by going to the double cover of S2 to get some genus 1 surface using this famous elliptic lambda map. And this was done in some famous papers in the 80s by these 4 gentlemen. I actually believe that when this paper was written, 2 out of 4 of these people were at Chicago, but maybe people in the audience can correct me if I'm mistaken. And what they did was, well, I'll just tell you what the final answer is. There's some stuff that comes along for the ride. And all of the moduli dependence is in this lattice theta function. So this theta function depends on the moduli of the theory. So here are your G fields. And the rest of this stuff is stuff that comes along for the ride. And what this is roughly speaking, the oscillator modes you get by taking when you go to the double cover. And I wrote this in terms of tau, not in terms of x, but these are related by this elliptic lambda map, which is what maps you from the double cover of the sphere to the torus. So the details of this construction don't matter. I just want to point out that there's some explicit formula for what this 4-point function is, which means that you can compute the average. And the only thing you need to average over is this lattice theta function. And so in fact, the same techniques that Siegel and et al. Used will give you this average theta function. So I'll just tell you what the answer is. Okay, the final answer is given by this expression, and it's not as scary as it looks. So let's go through this a little bit slowly. First, this is the moduli independent piece that sort of comes along for the ride. This is roughly just the oscillator modes. But what happens is there are 3 terms here, each with a delta function. So the first thing I want to point out is this 4-point function only is non-zero averaged when the operators are pairwise equivalent. So for example, imagine the first 2 operators were the same. So epsilon1 was equal to 0. Then this delta function in the second term would fire. And similarly, these 2 terms would be the same. Or if the first and the third operator were the same, then this delta function would fire. Or the first and the fourth, then this delta function would fire. So the first interesting statement is that if the operators are not pairwise equivalent, although it's the case that the 4-point function at every individual point of the moduli space is non-zero, when you average over the moduli space, they all cancel and give 0. So it's only non-vanishing when it's of the form like AABB. Okay, so what is this function E? This E of gamma 2 is a subgroup of SL2Z. It's defined this way, it doesn't particularly matter. But instead of summing over the modular group of all of SL2Z, we sum over the modular group of a subgroup of SL2Z. So why does this make sense? The reason is the following. Suppose the operators were of the form AABB, and then you did some modular transformation on tau, which corresponds to some crossing transformation on X in this map. If you exchange X with the operator located at X with, let's say, the operator located at 0, then you'll get the same correlation function if it's of the form AABB. But if you exchange X with 1, say, do a monodromy around 1, you don't get back to the same correlation function because these 2 operators are different. So this subgroup of SL2Z is precisely the subgroup that you would expect, given that these 4 operators are not identical. So the reason we don't, is what I said, the reason we don't get all of SL2Z, but rather some subgroup of SL2Z is because there are some elements of SL2Z that exchange these epsilons. Okay, so now I want to ask what the holographic interpretation of this average is. So let me rewrite the average correlator schematically. So let's get rid of like a bunch of this stuff. And roughly speaking, what we're doing, so here I wrote of the form, I made the first and the third operator the same. I guess you can't quite see the primes, but these operators are of the form AB, AB. And what we're doing is we're summing over 1 over eta of tau to the 2c. And we're doing the sum only over gamma of 2, which is what the subgroup of SL2Z that preserves this order of the operators are. Now, in the X variable, if you take monodromies of X around the point 0 or the point 1, it turns out this generates the group gamma of 2. So let me draw a picture for this. So in the bulk, so here's ADS3, we're going to sum over configurations of Z2 vortices. So let's say I have the 4 operators at the points 0, 1, X, and infinity. And 0 or 1 are the same. So there's some Z2 vortex connecting them. And there's some vortex connecting X and infinity in blue here. And this group gamma of 2, mod gamma infinity, is in 1-to-1 correspondence of monodromies of X around the point 0 and the point 1. So what we're doing is we're taking this point X and we're doing monodromies around 0 and 1, which will generate these sort of knotted configurations of the Z2 vortices. So what we're doing is we're summing over all of these different sort of loops of string between these 4 points, such as the following. These configurations of vortices are called, well, they're in general called tangles. And the special vortices, the special loops that can be obtained by moving the points on the boundary around each other are called rational tangles. So this on the left is an example of a rational tangle, and this on the right is not. So these 2 pieces of string on the right wrapped together, you can convince yourself that no sequence of monodromies of this X around these 4 points will ever sort of untangle these 2 knots. And the claim is that if you take any of these rational tangle configurations and take their double cover, because remember we have this Z2 vortex here, and we sum over all of these with the Chern-Simons action evaluated on them, then we will reproduce this correlation function on the right-hand side here. So now there's a question, which is what is the rule that tells us that we should include only configurations on the left here, but not on the right here? Right? Because we see that these ones that we call rational tangles, these are enough to get the right correlation function from the CFT. But what rule in the bulk is there that tells us we should sum only over only the tangles of the form that of the form on the left, but not on the right? And so to answer this question, I'm going to first take a brief digression and show you a brief video. So okay, maybe before I show that, I'll say in words what we're going to do. What we're going to do is we're going to look at what the geometry in the bulk is when we take the double cover of these tangles, where we remember that these these generate some holonomy of the gauge field. So really the bulk geometry is some double cover of this, because if you go through and you go around any of these tangles, the gauge field goes to a minus of itself. So the true geometry in the bulk is some double cover of this. And we'll see that these rational tangles have some very special geometric properties that these irrational ones do not when we look at their double cover. So I'm briefly going to now share 2 minutes of a video. So let me stop the share here. This is some technology. Okay, do people see my screen? This Yeah. Okay. So this is a video
Bill
by,
Thurston. Yeah.
Yeah. This is the video by Bill Thurston. I'm just going to play two minutes of this video. But for those of you who have time, I recommend that you watch the whole thing. It's well worth watching.
I want to take you through a little exercise of the imagination that will help understand and distinguish different kinds of knots. So we're going to begin with the most ordinary knot of all, the unknot. Here's a unknot in the form of a loop of tubing. But what you may not realize right away is that this tubing has magical properties. It creates a singularity in the fabric of the universe. And what it does is that if you look through the tubing, the universe you see through the tubing gradually drifts away from the universe on this side of the tubing. And over many years, its properties and its occupants change a lot. That world through the tubing is called Narnia. I can step through this magical loop. It's like a doorway into another world, the world Narnia. Here we are in Narnia. We've been exploring, we've had lots of adventures and seen many unusual and interesting sights, but we've arrived finally back at this coil, this unknotted coil, and when we look through it again, we see Earth. I'm kind of tired of being in Narnia, so I'm going to step through the coil, and I'm back in Earth again. This tubing creates a two-way branching in the universe. When I go through it once, I go from Earth to Narnia. If I go through it again, I go from Narnia back to Earth. I can keep going as many times as I want, from Earth to Narnia. And it doesn't matter which direction I go through. I went from Earth to Narnia. Here I'm in Narnia, and I can step back out, and I'm in Earth again, and so forth. This is the property of the tubing. But the tubing doesn't have to be just arranged as an ordinary kind of unknotted door. What happens if you knot the tubing? Will it create the same kind of split in the universe, or will it create a different kind of split? Well, let's try and find out.
Okay, can you hear me? Yeah, okay. So for the rest of the talk, Thurston then talks about what happens if you look at the double cover of some trefoil, and it's a very nice video. So for those of you who are interested, I highly recommend it. Indeed, as Thurston says, he studies the geometry, the three-dimensional geometry that you get by taking the double cover of these tangles. And now I'm just going to tell you a fact that distinguishes the rational tangles from these irrational tangles. If I can move to the next slide. Okay. There's a lemma which was proved in the 80s by Hodgson and Rubinstein, which says that if the double branch cover of a tangle is equivalent to a solid torus, that's true only if the tangle is rational. So the double branch cover of these give us a solid torus, which are precisely the geometries that we want to sum over in the ADS3. But the double branch cover of this gives us some much more complicated non-handle body geometry, which does not admit a hyperbolic metric. So the sum over geometries in the bulk theory is equivalent to the sum over rational tangles, because these are the ones whose double cover gives us a hyperbolic metric. And that is precisely the modular sum that we need to reproduce, that we need to do in order to reproduce this average correlation function. I did this for Z2 orbifolds. We can look at ZP orbifolds as well, like we did in the previous slides. There, it's a little bit more complicated because now instead of looking at the double branch cover, you'll need to look at the N branch cover. But there's actually a theorem which was proved, well, the proof was sketched by Thurston, that the N-fold cover of a two tangle is a genus N-1 handle body, if and only if the tangle is rational. There's actually a subtlety here because there exist non-handle body hyperbolic geometries in whose boundary is a higher genus Riemann surface. So it's not entirely clear what to do with those. And this subtlety also was present in the original papers by Nima et al. And Alex et al. So it's not clear from the ADS-CFT side why the handle body geometries should be preferred for these ZP orbifolds. Well, I'll be happy to discuss that more, but I think it's an interesting open problem. Okay, so for the rest of the talk, I'm going to talk about more complicated control manifolds, but maybe this is a good time to stop if there are questions before we go in a different direction. Okay, so far in this talk, we've been averaging free theories and their orbifolds and their partition functions, correlation functions, etc. But these theories are all a little bit boring because they're free. And it's well known that free theories are not the only theories with conformal manifolds. In general, of course, if you have a 1,1 operator, this operator is not protected in general, and there's no reason that you'll get a conformal manifold, because if you deform by it, then this operator will no longer be marginal. So it's not going to be an exactly marginal operator. But there are sort of two classes of theories which have these exactly marginal operators. One are the free theories, which we've been studying, but there's another class of CFTs which have exactly marginal operators. And those are supersymmetric theories, in particular theories with at least 2,2 supersymmetry. I'll just say this fact, which is if you take half BPS states with the appropriate charges, then you can show that these are marginal operators that are exactly marginal. They're protected. These are sometimes called operators in the CC or AC rings. So this gives us a much more complicated moduli space that in principle we should be able to average over. And so in the rest of this talk, I'm going to ask, can we average over these moduli spaces? And if so, what do we get? And as a spoiler, I'm not going to succeed, but so I'm not going to be able to tell you what the average is, but I'm going to be able to tell you what the average is not, which is, maybe almost as good. So let me just give a little bit of background for people who may not be so familiar with this. I'm going to consider two examples, the K3 CFTs and Calabi-Yau threefold CFTs. So for those who don't know much about this, I'm just going to tell you some facts about them that I'm going to use. So K3 is some central charge 6 superconformal field theory. It has n equals 4,4 supersymmetry. And it comes with a moduli space. There's not just like one K3. There's an 80-dimensional moduli space of K3 CFTs that we can look at. And it comes in this double coset. You can check that 4 times 20 is 80. So this is some large moduli space, and K3 is some complicated interacting theory. At some generic point, at some random point in the moduli space, we certainly do not know what the spectrum is. Unlike the case for Narain theories. There's some special points where we do know the spectrum, like Gepner models or T4 mod Z2 orbifolds, but at generic point, we don't know the spectrum. but it may be the case that the average spectrum is easier to understand than any particular point. Okay, similarly for Calabi-Yau threefolds, this is now a central charge 9. There's only 2, 2 supersymmetry. And now the moduli space takes some factorized form. And the dimensions of these moduli space depend on the number of half BPS states in this Calabi-Yau threefold. And the half BPS states, the number of half BPS states we call H11 and H21. So these are some non-negative integers. So one very reasonable question to ask is, what's the average K3 partition function, or what's the average Calabi-Yau threefold partition function with fixed H11, H21? So in other words, so let's take some connected Calabi-Yau moduli space and ask what the average partition function is there. Okay, so the usual trick, the argument of Siegel and that was used by Nima and friends does not work here. So I didn't really tell you why, but let me really kind of sketch the argument. What they did was they showed that the average partition function has to obey a specific differential equation. And the reason on a technical level they were able to do that was because the stress tensor was built completely from the U1 currents for free bosons. So the stress tensor is just dxi dxi, dd bar xi. So it's kind of like the Sugawara stress tensor. And if the stress tensor takes that form, you can show that the average partition function obeys a particular differential equation that has a unique solution. And that's not going to be true for K3 or Calabi-Yau, but we can just try to guess the answer anyway. So one guess you may have is the average for the Narain theory was you take the vacuum character squared and you did its modular sum. So maybe we can just get lucky, and the average partition function is just the modular sum of the vacuum character squared. The vacuum character for Calabi-Yaus and K3 is known. These are the n=2 and n=4 superconformal algebra, and they were computed in the 80s. And so we can just compute the right-hand side and just cross our fingers and hope that this is the average K3 or Calabi-Yau partition function. However, we know that the answer will turn out to be no, because if you do this, you don't get a positive definite spectrum in the modular sum. So let me say that in a little bit more detail. If you take the n=2 or n=4 vacuum character and do its modular sum, and then take its inverse Laplace transform, then you'll get the average spectrum. And whatever the average spectrum is, it had better be non-negative everywhere, because you're averaging a bunch of positive or positive quantities, and the average of a bunch of positive quantities is always positive. So unlike in the U1 to the C times U1 to the C chiral algebra, if you do this calculation, you do not get a positive definite spectrum. The spectrum is negative. Actually, this is a very similar phenomenon that happens if you do the same calculation for any of the following chiral algebras: Virasoro for C bigger than 1, n=1 for C bigger than 3/2, or Wn for C bigger than n-1. So we checked a bunch of these examples. I don't have a proof of the following statement, but it's very natural to conjecture the following. Any chiral algebra where the central charge is bigger than the asymptotic growth of one of the vacuum character will not have a positive definite modular sum. I think this would be quite interesting to prove, but I don't know how to prove it.
Nathan.
Yes.
So I thought you said that one of the points in the moduli space was T4 mod Z2,
That's
which
right.
fell in the class of things you did do this sum over and didn't get any negative states.
Very good. So if you restrict yourself to the T4 mod Z2, so T4 mod Z2 is some sublocus, some 16-dimensional sublocus of K3 moduli space. And if you restrict yourself to that sublocus, then the generic chiral algebra is bigger than n=4. It's in fact the chiral algebra we were discussing earlier, well, with the fermions. So if you average over a sublocus of K3, which has this enhanced symmetry, which the T4 mod Z2 locus does have, then the story is very different. And then indeed we know what the average is from our orbifold computation. But here I'm asking something more ambitious. I'm asking, can we average over all 80 dimensions? And the shared chiral algebra in the 80-dimensional theory is not the chiral algebra of T4 mod Z2, it's just the n=4. And if you just take the n=4 vacuum character and take its mod squared, then you don't get a positive definite spectrum. By the way, the T4 mod Z2 subalgebra does not have this property that C is bigger than C currents. Their C is 6, but the C currents is also 6. Okay, so this was one wrong guess. The wrong guess being take the modular sum of the vacuum character. No, sorry, this is just what I said. We don't know what the average is, but its spectrum is better be positive definite, so it's not this. Okay, but as we just spent the past 30 minutes discussing, in order to get, for the orbifold theories, in order to get the right average partition function, we didn't just look at the vacuum character squared, we had to look at all moduli independent pieces. So for the orbifolds, we had to include the twisted sectors, which were moduli independent. So maybe we also need to look at the moduli independent pieces for the supersymmetric theories. So what are moduli independent pieces for the supersymmetric theory? Those are the BPS states. So some quick facts about BPS states for those who are not as familiar. In these theories, there are two types of BPS states that we'll call half BPS states and quarter BPS states. These half BPS states are completely protected everywhere in the moduli space. But the quarter BPS states are not quite. What's only protected for the quarter BPS state is some signed count. So like the sort of bosons minus fermions. And the quarter BPS states, their total number can change, but in a sort of coordinated way such that their signed count remains the same. The signed count is something that's called the supersymmetric index, or in this context, the elliptic genus. And this one is protected. But there's an accident that happens at low central charge for both K3 and for Calabi-Yau threefolds, which is that actually for these two theories, it turns out that the quarter BPS spectrum is basically uniquely determined. And what I mean by basically uniquely determined is that if you make a very mild assumption that the chiral algebra generically does not enhance, then the quarter BPS spectrum is uniquely determined for K3 and determined as a function of the half BPS spectrum for Calabi-Yau threefolds. Okay, that was some technical aside, but the point is that now there's another prescription we can try, which is instead of taking the modular sum of just the vacuum character for K3 or Calabi-Yau threefolds, let's try taking the modular sum of all BPS states for either K3 or for Calabi-Yau threefolds. Maybe that's the average partition function, given our intuition that we learned from the orbifolds in the first half of this talk. Okay, surprise, it doesn't work. If you do that computation, you take the modular sum of all moduli independent pieces, meaning all BPS states for either of these two theories, you again do not get a positive definite answer. So therefore, whatever the average is, it's not equal to this. So this observation that the average partition function is the modular sum of the moduli independent pieces does not appear to generalize to interacting CFTs. I think it would be very, very interesting if we can somehow compute what the average K3 CFT is. I think there are many situations where the average is simpler than any individual component. So one example is, in fact, in these Narain theories. I guess I didn't mention it, but this average Narain theory is much, much simpler than any individual Narain theory. More generally, the fact that averages are simpler to understand is like, I think, the basis of all of statistics, if I'm not mistaken. But I don't know, I think this would be maybe an interesting line of research to pursue. So let me just summarize since I have just about a minute left. So in this talk, we generalized this Narain average holographic duality to the case of a Z2 orbifold CFT. There, the average is now no longer just the modular sum of the vacuum character, but rather all moduli independent pieces. And we also did the ZN orbifold. The moduli space was different there, but again, we got a very similar phenomenon. We did some holographic interpretation of both, and we also gave a holographic interpretation of the average of twist operators for both the Z2 and the ZN case. But many statements about averaging do not appear to generalize to supersymmetric conformal manifolds, and I think that would be extremely interesting if we could somehow make progress on that question. And with that, I think I'll finish. So thank you very much for your time.
Thank you very much, Nathan. I guess maybe we have time for a quick question before we stop recording. If anyone has any urgent questions.
What about averaging? Oh, go ahead, Jeff.
It's not urgent, but yeah, I was going to ask, what about averaging? Well, I guess C equals 1 is not a good example because it diverges, but nonetheless, at C equals 1, we have the circle line, we have the orbifold line, and we have the 3 points, which are sometimes called the Ginzburg archipelago. Yeah. You might ask, what if I just averaged over all C equals 1 CFTs? Or at least, I don't know if there's a proof that that's all, but I think it's believed to be the case. Anyway, one could ask something similar in higher dimensions, I guess, averaging over all conformal field theories with given central charge rather than given chiral algebra. That's
a great question. Well, let me just make a comment first about the C equals 1 example, which is that of course, you can in principle average over both the S1 and the S1 mod Z2 branch. Well, okay, modulo the divergence, but whatever. But I guess as you were alluding to in the end of your question, the shared chiral algebra differs there. So it's not entirely clear what that would mean, because now you're gonna sort of half of your theories will have one chiral algebra and half of them will have another chiral algebra. In principle, you could do it. I don't know what the interpretation would be. As for higher dimensions, I think in principle, I think you should be able to do it as well. So for example, n equals 4 super Young mills, in principle, there's some, I don't know what the interpretation would be, given that we know what the dual is and it's not an average. But in principle, you could average over like the moduli space for tau, the kinetic term, and indeed that moduli space is H mod SL2Z. So maybe there's some interesting observables that'll happen if you average over that. But in practice, it's probably very difficult to compute that in the extremely strongly coupled regime where tau is like an order 1 number. But I think in principle, that would be very interesting.
Okay, thanks. I'll stop the recording. It can take a couple minutes.